Right, so this is probably, as you guessed, about EMF. Now, the first question you've got to ask yourself is, what is EMF? Well, EMF is something called electromotive force. So, put that down. Electromotive force. I just put electric motive F because I'm quite lazy. Right. So, what is electromotive force? Well, it's the electrical energy produced per unit charge. And you should be starting to think a little bit about what an equation could look like. So, if it's electricity produced per unit charge, yeah, then it's going to be, the formula is going to be total amount of electric force, or yeah, produced over the charge. If it's per unit charge, you look at the amount of charges, you divide it by that amount. So yeah, so the source of electrical, yeah, so sorry, just checking, that was the electrical energy, not force, I said that, electrical energy. Now, it's all very well and good saying, yes, electromotive, that sounds intelligent. So, how can we link this into our other topic of internal resistance? Well, internal resistance, let's put internal R, equals EMF, take PD across terminals. So PD across terminal is the same as saying V equals IR. So it's a main potential difference that you need to worry about. So your internal resistance, well, what is that? Well, you can have an external resistor, a resistance in the form of it could be a variable resistor or any type of resisting material. However, the internal resistance is, I have said internal resistance of the material. Now that is more the actual internal resistance. External resistance is anything you add onto the circuit. The internal resistance is, say, the resistance from the wires, for example. So, just to give you a bit of a guide there. So yeah, EMF, we can describe what EMF is. Hopefully you've understood what the potential difference across terminals is. So, yeah, that is the basic stuff. Now I'm going to rub this off and yeah, hopefully you've got that down. Just, yeah, there. So what we're going to go on to now is we're going to give you a bit of a scenario about how we can use this theory of electromotive force. So we'll say we've got a battery here. Just copying it from the diagram here. Yeah, so we've got a internal, when you see something like it looks like a resistor, except I don't know if you can quite see it on there. Let me come on and see if I can see it on the camera. Yeah, well, it's got a little R. Now that little R doesn't mean little resistor. What it means is the internal resistor. So it's not specified in one place. It looks like it is on there. It's spread across the material, with the wire, say for example. And this is connected to a large resistor. Now I could put these anywhere on the circuit. I'm just choosing them to put them here. I would say you wouldn't create a series. You wouldn't create a parallel loop circuit. That's one cell. The circuit. Obviously, you're more likely to have a battery in this case, but I'm just going to, just give you an example. So, just going to put it out there that electromotive force is equal to the potential difference. That is just something you need to know. I'm not going to spend too much time going into that because I'm going to try and keep this a bit short. So, E equals F, so E equals V. So we know V equals IR. We substitute E into that, so we've got E equals IR. hopefully you're just going along with what I've said. And now if you want to know the total resistance, so is from, we'll do it now, okay, we'll do it in this video. So to work out the resistance of a series, basically what we do is we add the individual resistors up. Now I'm not just going to say that, I'm actually going to demonstrate it to you now. So I'm going to demonstrate how we work out R for this is a series circuit. So we can add up the potential differences because they're not the same in a series circuit as like a parallel. So we have to assume they're different. So V equals V1 plus V2. This we'll just call this V1 and V2. Now V1 and V2, they're just different potential differences. I've just given them V1 or V2. You could call them V7 and V8 just to confuse you. But so V, as we said, is equal to IR. Now I'm just going to assume we're just going to work with V instead of E, just for the moment. So as the current doesn't change as it's in one circuit, which unlike it does in parallel, V is equal to IR1 resistor 1 plus IR2 from resistor 2, which is that one. Now, as we know, if we want to find out the resistance, we can change this into R equals V over I. We've got the resistance here, so if we do V over I, we just cancel out these two, the two I's on top, and that means R is equal to R1 plus R2. And that's how you get the resistance in the, so the R at the end, that is like the sum of the resistances. So hopefully you've understood how we've kind of got that there. I don't know if you can see the bottom left. Hopefully that's quite self-explanatory to you and me. Hopefully it comes across that way anyway. So that is that is just proving to you how you get a resistance or something. Sorry. Yeah, sorry about that. Right, okay. So that's how we do that one. Okay, so let's go back to this equation. We've got I equals E over R. Now R is the sum of the resistances, and as we've said, it's just R1 plus R2. Am I going down the right lines here? Yeah, so we could put R plus R, and small r is the internal resistance. And then we can expand this, so move that over to that side by times in both sides. So that becomes, when we expand it, IR plus IR, small resistance, equals electromotive force. Now there's a couple of things we can do with that. To get the power, because power is equal to IV, we can times the whole equation by I, because E is equal to V, so if we times it by I, we get IV at the start, it's the same as IE. So we have to times the rest of the equation by E, and that gives us the power of the circuit. So let's do that. IE equals I squared, because we've already got R here, I squared times R plus I squared times little r. Now, to get the power, that's the power of the overall circuit. To get power of a certain part of the circuit, we're going to assume that we're not counting the rest of the circuit. One part would be one certain resistor, for example. So we just use the I squared times big R bit. So IE equals I squared R. Now we can't just put a current in there, we have to know what it is. And we work it out by doing I equals E plus R plus the small r, the internal resistance of a circuit. So we could put IE equals E plus R over small r. Sorry, E over R plus big R. And obviously we need to square that. And we times that by the resistance of the resistor. Hopefully you can see that. If you can't, it's IE equals E plus R over R, and we square that. We square see top and bottom, and we times that by the resistance of the given resistor that we're testing. So hopefully that's sort of got to grips with you. I'm just going to rub out this power bit at the bottom, because I just need a bit of room to expand the E equals IR plus R. Now you may be thinking to yourself, if you've not seen it already, that I plus big R, I times big R, it's the same as a potential difference over a given, over the terminals. Now you may go, what's a terminal? Well, a terminal is not a new train station. Well, it is, but a terminal is the potential difference across, there's potential difference across terminals in the battery. So we could change that to V. So V plus I small r equals E. And then we could obviously rearrange this to get V equals E take IR. Now we'll give you the potential difference across the terminals. Well, obviously if there's no EMF, then it's just small I R. Hopefully you've understood that. Okay, that's pretty much electromotive force done. Now there are, as I said, I did go over another topic in that one there. Just to see. Yeah, if I've missed anything out, I will create another video, but I don't think I have. Oh wait, actually, sorry, just forgot something. Just remembered. Right, can't miss this out. So we've got the equation E equals I big R plus I times small r. You might go, well, we've already talked about that equation. Yes, but sometimes it asks you to go calculate the lost energy in a source. Now, you may go, oh, what? We don't have an equation for that. Well, you kind of do. So the internal resistance is the lost energy, so to speak, of what we're trying to find out. Now, that there is the lost energy. And as I said before, the big I and the small r, big I, big R, is the PD across terminals. So let me just check that before I say that's absolutely 100% correct. Looks like it. Sorry, just yeah. Terminal PD plus lost. Yeah, that's a lost, not lost energy, lost PD, sorry. Oh yeah, it'd be the lost energy, even. Same thing actually. So I hope that's given you an insight into this topic. I hope you enjoyed it, and we'll see you in the next video.